14.7 Part 1. In single variable calculus, we often need to do a change of variables in order to integrate. While the function and interval of integration change, the total area under the curve does not. Depending on the particular situation, we might write a change of variables as either u as a function of x or x as a function of u. In doing a double integral, if we want to do the same sort of task, we call it a transformation. With a transformation, there will be a change of functions and a change of region over which we integrate, but there will not be a change of volume. Suppose we wish to do this double integral of f over r. And to do the double integral, we are going to do a transformation. And our new region is S is closed and bounded, and our transformation involves continuous functions that have continuous first partial derivatives on S. And lastly, f is continuous on r. If all of those circumstances hold, what will be the new integral? Our new integral will look like this. Now I'm introducing a new function called the Jacobian. The Jacobian of uv is the determinant of a 2 by 2 matrix of partials. To see how we use this theorem, we're going to revisit a familiar change of variables into polar coordinates, which you've already done, going from Cartesian to polar coordinates and then doing a double integral over polar coordinates. So you already have done a problem like this. I would just like to do it again using our new theorem. And this is the set of steps that we're going to do. The first thing that we do is we find our old region. Looking at the integral in Cartesian coordinates, what is the region over which we are integrating? So look at the fact that y is going between 0 and the square root of 1 minus x squared, and that x is going from 0 to 1. What region does that describe? Perhaps you saw that it describes the quarter circle of radius 1 centered at the origin. Once you've done that, you need to find the new region S. Now, our new variables are going to be r and theta, so your new region has to be in terms of r and theta. I've put r on the horizontal and theta on the vertical, and you might have had it reversed, but really the important piece is that r is going from 0 to 1 and theta is going from 0 to pi over 2, and it's going from 0 to pi over 2 because it's a quarter circle, and r is going from 0 to 1 because the radius of the circle is 1. Now the transformation is not 1 to 1 on the boundary. Notice that the entire line segment D is mapped to the point D prime. However, the only thing that is required is that it be 1 to 1 on the interior, which it is. Our next step is to compute the Jacobian, and I have rewritten the Jacobian as a Jacobian of r and theta. When you're doing Jacobians on your own, you'll have to make the adjustment yourself. But I thought for this first time, I would make the adjustment for you. So find the determinant of partials, and then after you've done that, oh, I'm sorry, I meant to say find the matrix of partials, and then after you find the matrix, find the determinant. And did you get that the Jacobian is equal to r? Well, isn't that interesting? When we did double integrals of using polar coordinates, we needed to insert a factor of r. Well, I love that consistency. Our next step is to find the absolute value of the Jacobian times dA. Now dA is going to be in terms of r and theta. So dA now with our new variables, dA is equal to dr d theta. The absolute value of the Jacobian is just r because r is always non-negative. And next, we need to find our new integral. So we're going to make the complete change now. We're going to write a new integral using our new boundaries and our Jacobian times dA. And we also need to rewrite our function. And this is what we get. X squared plus y squared, when we make that transformation into polar, x squared plus y squared equals r squared. So this is our new function. Last step is to integrate. And this is what I get. I'm going to leave you here with this slide. Spend as long as you want with it, and I'll see you in part 2.